In section 1.6, I'd like to discuss with you absolute value equations and inequalities. The main idea behind solving these absolute value equations and inequalities is this. The absolute value of a number, like -2, can be thought of as the distance from -2 to 0 on the number line. So when I graph that on the number line, let's see, here's -2. -2 is 2 units from 0, which is one justification for why the absolute value of -2 is just +2, because it is 2 units from 0. Likewise, the absolute value of 7 is, let's see, 1, 2, 3, 4, 5, 6, 7. Well, 7 is 7 units away from 0. So the absolute value of 7 equals 7. And finally, the absolute value of 0 itself, well, 0 is 0 units away from itself. So the absolute value of 0 is perfectly okay. It's equal to 0. What's going to happen in this section is we're going to get problems like, for our first example, say we have to solve the absolute value of something like, I don't know, x equals 8. Well, we could have two possibilities for numbers whose distance is 8 units away from 0. Clearly, 8 is 8 units away from 0, but also -8 is 8 units away from 0. So we have two possible answers, 8 and -8. If these get a little bit more challenging, like in our second example, say we have to solve the absolute value of 3x minus 4 plus 2 equals 5. Okay, so what we're going to do first, kind of similar to our solving radical equations, we're going to subtract 2 first to isolate the absolute value. So 3x minus 4 equals 3. But there are two possibilities for what 3x minus 4 could be equal to if the absolute value of it turns out to be 3. Just like in the last example, x could be equal to 8, or it could be equal to -8. Those are two possibilities where we take the absolute value of that number and it spits out 8. So likewise for this problem, 3x minus 4 could be equal to 3, or 3x minus 4 could be equal to -3. Those two numbers on the inside, 3 and -3, when we take their absolute values, they will give us a 3. Okay, and now we have two relatively easy equations to solve. Adding 4 to both sides, we have 3x equals 7. So x equals 7/3. And adding 4 to both sides of this equation, we have 3x equals 1. So x equals 1/3. So frequently when we solve these absolute value equations, we have two different answers. And also frequently, because the motivational example at the beginning is the positive and the negative of the same number, people think that it's going to be one positive and one negative. But this is a great example to show you, no, you could have both negatives or both positives or one of each, but you are frequently going to have two answers, one from when the inside is equal to the positive of this number, and the other from when the inside is equal to the negative of this number. Okay, let's try a couple more examples. So let's solve the absolute value equation, absolute value of x over 4 minus 1 over 5 equals 3. Okay, The absolute value has already been isolated, so I'm going to break this apart into two equations. One where x over 4 minus 1 over 5 equals positive 3, and the other one where x over 4 minus 1 over 5 equals negative 3. And solve each one of those. Great. In both of them, we can clear fractions. The common denominator between 4 and 5 is a 20. So we'll multiply everything we have here by 20, and that will give us 5x minus 4 equals 60. Okay, so 5x equals 64, so x is 64 divided by 5. And we're going to do exactly the same thing on the other side. When we multiply everything by 20, just as we did before, we still get 5x minus 4. Now it's equal to negative 60. So when we add the 4 to both sides, we have 5x equals negative 56. And dividing both sides by 5, x equals negative 56 over 5. Terrific. Okay, let's see how these can get maybe a little more challenging. So let's solve absolute value of the quantity 3x over 7 minus 1/12, then plus 4 equals 1. Well, now your first step should always be to isolate that absolute value sign. So absolute value of the quantity 3x over 7 minus 1/12 equals negative 3. Now there's a very important thing that you need to do at this point. Stop. Because you have an absolute value, rather ugly fractions with which to solve, and what you do not want to do is start setting 3x over 7 minus 1/12 equals negative 3, and another one equals to the positive 3. Whoops, that didn't look right. There we go. You don't want to do this because remember, we think of absolute values as distance to 0, and you can never have a distance with negative values. An absolute value, the smallest an absolute value could ever be equal to is 0. The absolute value could never be equal to negative 3. So you always want to stop and double check if you have a negative number on the other side from the absolute value, then you have no solution. Okay, well then let's try one that actually does have a solution. Okay, ooh, I'm not hopeful. Solve 9 minus the absolute value of 2x equals 5. Okay, so remember, you want to isolate your absolute value first, so we'll subtract 9 from both sides. That gives us negative absolute value 2x equals 5 minus 9 is negative 4. Now, the reason I don't want to stop here and say no solution is because, yes, I have a negative on the right-hand side with the negative 4, but I'm not done isolating the absolute value sign. So we need to divide both sides by negative 1 so that it cancels with the negative in front of the absolute value, giving us the absolute value of 2x equals positive 4. Since it's a positive 4, we can continue. So we get two equations. 2x equals positive 4, 2x equals negative 4. So x equals 2 and negative 2. Okay, let's try one more that's a little bit more Math 12 level. This is one of my favorite examples in this class. We're going to solve the absolute value of x squared plus 2x minus 4 is equal to 4. Now, first thing I want you to notice is the absolute value has been isolated, which is great, and we have a positive number that it's equal to, which is even better. So we must have two equations. We must have x squared plus 2x minus 4 equals 4, and x squared minus 2x minus 4, x squared plus 2x minus 4 equals negative 4. Okay, so two quadratic equations to solve. For both of them, same idea. I want to get 0 on one side. So we'll subtract 4 from both sides on the first one. X squared plus 2x minus 8 equals 0. That factors. X plus 4, x minus 2 equals 0. So x is negative 4 and positive 2. Okay, for the other equation, we're going to add 4 this time to both sides, making all the 4's cancel. X squared plus 2x equals 0. That factors by taking out a common factor of x, leaving us with x plus 2. So our two answers must be 0 and negative 2. Very cool. So this one, because we had a quadratic in our argument for our absolute value sign, we actually ended up with 4 answers needing to factor in both of them. Let's move on and start talking about inequalities now. So before we do some examples, full worked out examples on absolute value inequalities, I want to show you what pictures of the absolute value less than or equal to 6, and then in a few minutes, the absolute value of x is greater than, 4 look like on a number line. So let me draw a number line up here. There we go. Okay, so for the absolute value of x to be less than or equal to 6, that can be interpreted as the distance from 0 to x is less than or equal to 6. How about we say 6 units? Okay, so 1, 2, 3, 4, 5, 6. So x can be closer to 0 than 6 units. So x could be here at 1, or x could be at 4.5, or x could be at 3.1, or 5.9, or 6 itself, because it can be equal to 6. X can be any of these numbers whose distance is less than or equal to 6. X can't be over here at 8, though, because if x is all the way over there at 8, its distance from 0 to x is too big. It's 8 units away. Ooh, but I'm neglecting a bunch of them. X could also be on this side of 0, right? X could be at negative 1, or negative 2, or negative 2.3, or 3, 4, 5, 6. X could be way over here, too. So x could actually be right at 0. 0 itself is certainly closer to 0 than 6 units. So x could be absolutely equal to 0. It could be anything in here. And the way we would write this inequality right here is as a double or compound inequality, is all of our x's are between 6 and negative 6. So all of our solutions to this absolute value of x is less than or equal to 6 could be translated to be negative 6 is less than or equal to x, which is also less than or equal to 6. Or more concisely, x is between negative 6 and positive 6, and it can be equal to them. Okay, on the other hand, if we have a greater than sign, so the absolute value of x is greater than 4, then this can be translated to mean the distance from 0 to 4, or I'm sorry, 0 to x is greater than 4 units. So 1, 2, 3, 4. There's 4 units away. There's 4 units away, but the distance has to be greater than 4 units. So all of these x's would be out here. They would be further away from 0 than 4 units. They cannot be equal to 4 or negative 4 because we don't have an equality sign underneath our inequality sign. We did up here. That's why we can have these equal to each other, equal to the 6's at both endpoints. So what we would get for this one is the x's could be over here. It could go on forever, right? If x is way over here at 1,000, that certainly is farther away from 0 than 4 units. And if x is way over here at negative 10 million, that is definitely farther away from 0 than 4 units. So here is our problem with this inequality. I can't write this as a single statement because x isn't between negative 4 and 4, so I have to write it as 2 statements. One, x is smaller than negative 4, and the other one, x is greater than positive 4. Okay, so if I have a greater than sign, I have to split it up into 2. X can be smaller than negative 4, or x can be greater than positive 4. Okay, let's talk about this in regards to some specific examples. So if we're going to solve absolute value inequalities, we usually need to do 3 things. We usually are asked to solve, write our answer in interval notation, and graph our answers on a number line. You're not always asked to do all 3 things, but frequently you are. So first couple steps are the same as the previous ones. We still want to isolate the absolute value. So absolute value of 2x minus 3 is greater than or equal to, what, 3? If we subtract 4 from both sides? Okay, now here's what I want you to pay attention to. You're going to be asked to either split this up into 2 different inequalities or to write it as a compound inequality, and that will depend on what this sign is. If this sign right here is, as in this case, a greater than sign, it can have an equals to sign with it or not, but if it's a greater than sign, then you're going to split this up into 2 inequalities. One where it's greater than or equal to the positive, and one where it's less than or equal to the negative. So in this case, because we have a greater than sign, we're going to do exactly that. So 2x minus 3 is greater than or equal to 3. And we're also going to solve 2x minus 3 is less than or equal to negative 3. Okay, we have 2 small inequalities to solve. Shouldn't be too bad. So 2x is greater than or equal to 6. X is greater than or equal to 3. And on this other one, 2x is less than or equal to 0. So x is less than or equal to 0. Okay, so now I can put these 2 together on the number line. X is less than or equal to 0. Remember, equals to has a bracket associated with it. So x is less than or equal to 0 is there. And 1, 2, 3, x is greater than or equal to 3. That's right on top of 3. Goes that way. And the interval notation is negative infinity to 0, union 3 to infinity. So we have two separate parts for the inequalities, for the graph, two separate pieces for the graph, and two separate pieces for our interval. If you would like some extra practice writing inequalities in interval notation or graphing them, please don't hesitate to let me know and I can send you some other resources. In the meantime, let's practice one more example. So for this last example, let's solve the absolute value of 1 minus 3x plus 2 is less than 5. Okay, so just like in the previous ones, we need to isolate the absolute value, so we'll subtract 2 from both sides. Absolute value of 1 minus 3x is now less than 3. Okay, since this is a less than sign, so this symbol, or with the equals to sign, then you can write this as a compound or double inequality, like this. So we're going to go 1 minus 3x goes in the middle. It's less than 3, and it's bigger than negative 3. And these compound inequalities are great because we can solve basically two inequalities all at once. Just remember, whatever you do to one side, you have to do to all three sides. So if I want to, let's say, get rid of the 1 in the middle by subtracting, I just have to do it to all three sides. So that becomes negative 4 is less than negative 3x, which is less than 2. Likewise, I want to divide by negative 3 to get the x isolated in the middle. Now, this is kind of dangerous, and you might remember from inequalities that whenever you multiply or divide by a negative, you switch the direction of your inequality signs. If you have a compound or a double inequality, they will always both stay or both switch together. So we're going to divide everything by negative 3, giving us negative 4 divided by negative 3 is just 4/3. Negative 3x over negative 3 is just x, and 2 over negative 3 is negative 2/3. So there is our answer in inequality form. I always like to have it graphed. I think a graph is so much easier to use to get the interval. So let's see, negative 2/3 and positive 4/3. And if we look at this one right here, let's start with the 4/3. The x's, which are our solutions, are smaller than the 4/3. So the x's are smaller than the 4/3. At the same time, the x's are larger than the negative 2/3, so they're to the right of the negative 2/3. And since they don't have equal signs underneath them, we have parentheses. So as an interval answer, our answer would be parentheses negative 2/3, comma, 4/3, close parenthesis. So there's our graph, and there's our interval notation. And again, if you need a little review of interval notation and graphs and inequalities, just send me an email.